There is a star so immense, so staggeringly vast, that if you were to place it where our sun now sits, its outer atmosphere would swallow Mercury, Venus, Earth, Mars, Jupiter, Saturn, and continue outward still, engulfing the orbit of Uranus and reaching toward Neptune, devouring nearly everything we have ever called our solar system in a single, silent act of cosmic enormity. Its name is Stephenson 2-18, and among those who study the architecture of stars, it is sometimes called simply the Behemoth. It is, as far as our best telescopes and most careful measurements can tell us, the largest known star in the observable universe. Not the most massive, not the most luminous in every wavelength, but the largest, the most voluminous single stellar object ever confirmed by the instruments of human curiosity. And to understand what that means, to truly feel the weight of that single, astonishing fact, we must go on a journey. A journey not merely across space, though we will travel unimaginable distances, but a journey across the very nature of what it means to be a star, what it means to be enormous, and what it means to exist as a temporary arrangement of matter in a universe that builds cathedrals of fire only to let them collapse into silence. Let us begin where all such journeys must begin, with what we can see. On a clear night, far from the glare of city lights, you might look upward and see several thousand stars with your unaided eyes. Each one is a sun. Each one is a furnace of nuclear fusion, converting hydrogen into helium, helium into carbon, carbon into oxygen, building the periodic table one reaction at a time in the crushing pressure of its own gravitational heart. But from where you stand, on this small rocky world orbiting a modest yellow dwarf star, all those distant suns appear as points of light, dimensionless, interchangeable, a scattering of diamonds on black velvet. You cannot tell, simply by looking, which of those points is a star 10 times the size of our sun, and which is 1,000 times its size. You cannot tell which is a newborn blue giant burning to its fuel in a few million years of reckless brilliance, and which is a red dwarf so frugal with its hydrogen that it will still be shining when the universe is 100 times its current age. The sky does not reveal its scales easily. You have to earn them. And so humanity built telescopes. We ground lenses and polished mirrors and pointed them at the heavens, and slowly, over centuries, the true architecture of the cosmos began to reveal itself. We learned that our sun is a star, an ordinary one, middle-aged, middle-sized, middle temperature. We learned that it is roughly 865,000 miles across, a number so large it means almost nothing to the human mind without analogy. You could line up 109 Earths across the sun's face. You could fit 1.3 million Earths inside its volume. And yet, in the grand parliament of stars, our sun is unremarkable. It is a yellow dwarf, a G-type main sequence star, a perfectly respectable but thoroughly average citizen of the Milky Way galaxy. It is not small. There are red dwarfs that make it look enormous. But it is not large, not by the standards of what the universe is capable of building when gravity and hydrogen and time conspire in the right proportions. To find the truly enormous stars, you must look further. You must look to the red supergiants, the red hypergiants, those bloated, dying titans of the stellar world that have exhausted the hydrogen in their cores and expanded outward in a slow, magnificent, terminal swelling that transforms them from ordinary stars into something almost incomprehensible. These are the largest objects that natural processes can construct in our universe. Single, coherent, gravitationally bound structures whose outer atmospheres are so tenuous, so gossamer thin, that they blur the very boundary between star and space. And among all of them, across every survey, every catalogue, every infrared observation we have ever made, Stephenson 2-18 stands alone at the pinnacle of known stellar size. But before we travel to this colossus, before we attempt to wrap our minds around its dimensions, let us first understand why stars grow large at all. Let us understand the physics of gigantism, the forces that take an ordinary ball of plasma and inflate it to volumes that would dwarf entire planetary systems. Because the story of Stephenson 2-18 is not merely the story of one exceptional star. It is the story of what happens when the most fundamental force in the universe, gravity, meets its ancient rival, radiation pressure, and the two engage in a battle that can only end one way, in the star's destruction. Every giant star is a star that is dying. Every enormous crimson sphere hanging in the depths of space is a testament to the universe's most beautiful and most terrible truth, that the brightest things are always the most temporary, and that the price of magnificence is brevity. A star is born when a cloud of gas, mostly hydrogen, with a scattering of helium and trace amounts of heavier elements, collapses under its own gravity. This is the most natural thing in the universe. Gravity is patient. Gravity is persistent. A cloud of gas drifting through the interstellar medium might remain stable for millions of years, but eventually something disturbs it. The shock wave from a nearby supernova, the tidal forces of a passing molecular cloud, the gentle pressure of starlight from a neighboring stellar nursery, and the collapse begins. Once it starts, it accelerates. The denser the cloud becomes, the stronger its gravitational pull, the faster it draws in more material, the denser it becomes. This is a runaway process, a positive feedback loop, and at its center, a protostar forms, a knot of gas growing hotter and denser by the hour. When the temperature at the core of this collapsing knot reaches approximately 10 million degrees Kelvin, something extraordinary happens. Hydrogen nuclei, protons, stripped of their electrons, are moving so fast, colliding so violently, that they overcome the electromagnetic repulsion that normally keeps them apart. They fuse. For hydrogen nuclei combine, through a series of intermediate steps, to form one helium nucleus, and in the process, a tiny amount of mass is converted into energy according to Einstein's most famous equation. This energy, this flood of photons pouring outward from the core, creates an outward pressure that halts the gravitational collapse. The star reaches equilibrium. It is now a main sequence star, a stable, self-regulating fusion reactor, and it will remain in this state for as long as it has hydrogen to burn. For a star like our Sun, this main sequence phase lasts about 10 billion years. We are roughly halfway through ours. But for more massive stars, stars born with 10, 20, 50, or even 100 times the mass of the Sun, the main sequence lifetime is dramatically shorter. This is one of the great paradoxes of stellar physics. You might think that a star with more fuel would last longer. But the opposite is true. Massive stars burn their fuel not merely faster, but catastrophically faster. A star with 10 times the Sun's mass does not live 10 times as long, or even the same amount of time. It lives roughly 1,000th as long. The core temperature of a massive star is so extreme, the pressure so intense, that nuclear fusion proceeds at a furious, almost reckless pace. These stars are the prodigals of the cosmos, burning through their inheritance in a few million years, a blink of an eye in cosmic time, while their more modest siblings will shine for billions, even trillions of years. And when a massive star exhausts the hydrogen in its core, its story does not end. It enters a new phase, a phase of expansion, of transformation, of slow and magnificent dying. Without the outward pressure of hydrogen fusion to support it, the core contracts. It grows hotter, denser, and when the temperature reaches approximately 100 million degrees Kelvin, a new fusion reaction ignites. Helium begins to fuse into carbon. This helium burning releases energy, but it also changes the structure of the star profoundly. The outer layers, no longer supported by the same equilibrium that maintained them during the main sequence, begin to expand. The star swells. Its surface cools as it grows, shifting from blue-white or yellow to orange, and then to deep, smoldering red. It becomes a red giant, or, if it was massive enough to begin with, a red supergiant. And if it was truly, extraordinarily massive, it becomes something even more extreme, a red hypergiant. This is the category to which Stephenson 2-18 belongs. It is a red supergiant, possibly a red hypergiant, though the boundary between these categories is not always crisp. What is certain is that it is enormous beyond easy comprehension. Its estimated radius is approximately 2,150 times the radius of our Sun. Let me say that again, because numbers of this magnitude tend to slide past the mind without leaving a mark. If our Sun were the size of a basketball, Stephenson 2-18 would be roughly the height of a 50-story building. If you could somehow stand on its surface, which you could not, because it has no solid surface, only an ever-thinning atmosphere of gas that gradually fades into the void, and if you could travel at the speed of a commercial airliner, it would take you more than 1,000 years to fly around its equator once. Light itself, traveling at 300,000 kilometers per second, takes over 8 hours to travel from one side of this star to the other. 8 hours. Light crosses our entire solar system, from the Sun to Pluto, in about 5.5 hours. Stephenson 2-18 is larger than the orbit of Saturn. Consider what that means. If you were to remove our Sun and place Stephenson 2-18 at the center of our solar system, Mercury would be deep within the star's interior, a memory dissolved in plasma. Venus would be gone. Earth, this pale blue dot, this cradle of every life form we have ever known, would be consumed, orbiting not in the cold vacuum of space, but somewhere inside the tenuous, superheated outer layers of an alien atmosphere. Mars gone. The asteroid belt absorbed. Jupiter, the largest planet in our solar system, a world so massive it could contain over 1,000 Earths, would find itself well within the boundaries of this star. Saturn, with its magnificent rings, would be engulfed or barely grazing the surface. Only Uranus and Neptune, those distant ice giants orbiting in the frozen outer reaches of our solar system, might find themselves beyond the star's photosphere, looking inward at a wall of glowing red gas where their entire planetary family used to be. This is the scale we are dealing with. This is the Behemoth. But how did we find it? How do you discover a star that, despite its enormous physical size, appears as nothing more than an anonymous infrared smudge in an already crowded region of the sky? The story of Stephenson 2-18's discovery is, like so many stories in astronomy, a story of patience, persistence, and the slow accumulation of knowledge across decades of observation. It begins not with the star itself, but with the star cluster in which it resides, a massive, heavily obscured stellar association known as Stephenson 2, located in the direction of the constellation Scutum, deep within the Scutum Centaurus arm of the Milky Way galaxy. The cluster was first catalogued by the American astronomer Charles Bruce Stephenson in 1990 as part of a survey of heavily reddened stellar groupings in the galactic plane. Stephenson was a methodical observer, a compiler of catalogues, the kind of astronomer whose work forms the unglamorous but essential foundation upon which all subsequent discoveries are built. He identified a grouping of luminous, highly reddened stars whose light had been dramatically altered by passage through vast clouds of interstellar dust, and assigned it a number in his catalogue. Stephenson 2. At the time, the individual stars within the cluster were not well characterized. Their distances were uncertain. Their true luminosities were unknown. They were, in a sense, hidden, veiled by the very galaxy in which they lived. It was not until years later, with the advent of more powerful infrared telescopes and more sophisticated techniques for piercing the veil of interstellar dust, that the true nature of Stephenson 2 began to emerge. Infrared light, with its longer wavelengths, can penetrate dust clouds that are opaque to visible light. It is like switching from a flashlight to a heat-sensing camera in a smoke-filled room. Suddenly, objects that were invisible become visible. And when astronomers turned their infrared eyes towards Stephenson 2, they found something remarkable. The cluster contained an unusually high concentration of red supergiants. Not just one or two, but many, a whole congregation of enormous, evolved, dying stars, all born from the same primordial cloud of gas, all aging together, all approaching the ends of their nuclear burning lives in a slow, coordinated march toward oblivion. Among these red supergiants, one stood out. Stephenson 2-18, also designated as Stephenson 2 DFK1, or sometimes simply ST2-18, was the most luminous and, as subsequent measurements would suggest, the most physically extended member of the cluster. Its infrared brightness was staggering. Even through the dimming effects of interstellar dust, and the dust toward Stephenson 2 is prodigious, absorbing and reddening the light of every star behind it. ST2-18 blazed like a bonfire seen through fog. When astronomers corrected for this dust extinction, accounting for all the light that had been absorbed and scattered on its long journey to our telescopes, the intrinsic luminosity of Stephenson 2-18 turned out to be something like 440,000 times the luminosity of our Sun. 440,000 suns. Imagine taking every photon our Sun produces in a second, enough energy to power human civilization for millions of years, and multiplying it by nearly 500,000. That is the power output of this one star, radiating quietly, relentlessly, into the void. But luminosity and size, while related, are not the same thing. A star can be extraordinarily luminous, but relatively compact. The most massive blue supergiants, for example, are tremendously luminous, but only a few tens of solar radii in size. What makes Stephenson 2-18 extraordinary is not just its luminosity, but its temperature, or rather, its lack of temperature. It is cool. Its surface temperature is estimated at roughly 3,200 Kelvin, less than 60% of the Sun's surface temperature. And because luminosity is determined by both size and temperature, a star radiates energy proportional to its surface area multiplied by the fourth power of its temperature. A star that is very luminous but very cool must be very, very large. The only way to produce that much light at that lower temperature is to have an absolutely enormous radiating surface. The Stefan-Boltzmann law demands it. The physics is unambiguous. If you know the luminosity and you know the temperature, you can calculate the radius. And when you perform that calculation for Stephenson 2-18, you arrive at a number that strains credulity. Approximately 2,150 solar radii, give or take several hundred, depending on the exact values used for luminosity and effective temperature. Let us pause here and acknowledge the uncertainties, because honest science demands it. The size of Stephenson 2-18 is not known with the precision of, say, the size of our Sun or the distance to the Moon. It is an estimate, a well-constrained estimate, supported by multiple lines of evidence, but an estimate nonetheless. The distance to Stephenson 2 is not perfectly known. Various studies have placed it between roughly 18,000 and 20,000 light-years from Earth, with some estimates extending further. The interstellar dust extinction along the line of sight is significant and introduces additional uncertainty. The effective temperature of the star's photosphere, if photosphere is even a well-defined concept for such a tenuous, extended atmosphere, is difficult to measure precisely. And the star itself may be variable, pulsating, shedding mass, changing its apparent size over timescales of years or decades. All of these factors introduce error bars. The true radius of Stephenson 2 to 18 might be somewhat smaller than 2,150 solar radii, or it might be somewhat larger. What is robust, across all reasonable assumptions, is that it is one of the largest, if not the very largest, star currently known to science. It competes for this title with a small handful of other extreme objects, UI Scuti, WHG 64, BY Canis Majoris, Inmel Cygni, and depending on which measurements you trust and which analysis techniques you prefer, different stars may claim the crown at different times. The ranking of the very largest stars is a living, evolving list, updated with each new observation, each new distance estimate, each new dust correction. But Stephenson 2 to 18 has occupied the top position, or very near it, for years now, and its claim remains strong. Let us talk about those other contenders for a moment, because each of them has its own story, its own grandeur, its own lessons to teach about the nature of stellar enormity. UI Scuti, located in the constellation Scutum, the same general direction as Stephenson 2, though not in the same cluster, was for a time widely cited as the largest known star. Early measurements suggested a radius of approximately 1,708 solar radii, which would make it roughly as large as Saturn's orbit. But subsequent reanalysis, using updated distance estimates from the Gaia Space Observatory and revised effective temperature measurements, has revised its radius downward, perhaps to around 1,400 or 1,500 solar radii, still enormous, but no longer the record holder. This is the nature of the field. As our measurements improve, our understanding shifts. Stars do not change size because we measure them differently, but our knowledge of their size does, and humility in the face of these revisions is the hallmark of good science. DY Canis Majoris is perhaps the most famous of the red hypergiants, at least among the general public. It is featured in countless popular science videos and infographics, those dramatic size comparison animations where the camera zooms out from Earth to the Sun, to Sirius to Betelgeuse, and finally to VY Canis Majoris, each star dwarfing the one before in a vertiginous demonstration of cosmic scale. DY Canis Majoris is indeed vast. Its radius is estimated between about 1,400 and 1,700 solar radii, depending on the study, and it is also one of the most luminous stars in the Milky Way, with a luminosity that may approach or exceed 300,000 times that of the Sun. It is also actively dying in a spectacular fashion, shedding mass to enormous eruptions and asymmetric outflows that have created a complex, beautiful nebula of ejected material surrounding the star. When BY Canis Majoris finally exhausts its nuclear fuel, it is expected to explode as a supernova, perhaps even a hypernova, in a cataclysmic event that will briefly outshine its entire host galaxy. But that day is still thousands, possibly tens of thousands of years away. For now, it simply burns and swells and sheds itself into the void, a red ember the size of a solar system. WHG 64 is another extraordinary red supergiant, notable for being located not in the Milky Way but in the Large Magellanic Cloud, a satellite galaxy orbiting our own at a distance of about 160,000 light-years. Its radius has been estimated at approximately 1,500 to 1,800 solar radii, and it is surrounded by a thick torus of dust, material it is shed from its own outer layers over millennia. WHG 64 is interesting precisely because it is extragalactic. Its distance is better constrained than many Milky Way red supergiants, because we know the distance to the Large Magellanic Cloud with reasonable precision. This makes its luminosity estimate more reliable, which in turn makes its size estimate more robust. It is a reminder that the universe builds these colossal stars not just in our galaxy but everywhere, wherever conditions permit, wherever the raw materials come together in the right proportions, wherever gravity and nuclear physics can conspire to construct a ball of plasma larger than a planetary system. And Mel Cygni, located in the constellation Cygnus at a distance of roughly 5,500 light-years, is another member of this exclusive club of the very largest stars. Its radius has been estimated at around 1,650 solar radii, and it is an extreme red supergiant with a very high mass loss rate, expelling material into a surrounding nebula at a remarkable pace. Like all of these titans, Mel Cygni is a star that is living on borrowed time, a nuclear furnace that is burned through most of its fuel, and is now in the final stages of its life, swelling and pulsating and shedding as it approaches the inevitable conclusion. But among all of these, Stephenson 2 to 18 stands apart. Its estimated radius exceeds them all, 2,150 solar radii, with some analyses suggesting it might be even larger. If this estimate holds, it would make Stephenson 2 to 18 roughly 10 billion times the volume of our Sun 10 billion. The number is so large that it has no intuitive meaning. Your mind cannot hold it. You can say it, you can write it, you can calculate with it, but you cannot feel it. And yet it is a real number, describing a real object, hanging in real space, burning with the power of nearly 500,000 suns, located about 20,000 light-years from where you sit right now, reading these words. To begin to feel this scale, we need analogies. We need bridges between the cosmic and the comprehensible. So let us try a few. Imagine that you could fill Stephenson 2 to 18 with Earths. Not line them up in a row. Fill the entire volume of the star with Earth-sized spheres. You would need approximately 5 quadrillion Earths. 5 followed by 15 zeros. That is more Earths than there are grains of sand on all the beaches of our planet. Every grain of sand on every beach on Earth, replaced by an entire world, and you still would not fill this star. Or consider time. If you started counting from the number 1, counting one number per second, without sleeping, without eating, without pausing, it would take you approximately 158 million years to count to 5 quadrillion. That is longer than the time that has elapsed since the dinosaurs went extinct. You would begin counting in the Jurassic and finish sometime well into the future, and each number you counted would represent one Earth, packed inside a single star. Or consider light. Light is the fastest thing in the universe. Nothing with mass can ever reach its speed. It crosses the vast, empty gulfs between the stars as the swiftest possible messenger. And yet, as I mentioned, it takes over 8 hours for light to cross from one side of Stephenson 2 to 18 to the other. If you were standing on one edge of this star, hypothetically, impossibly, and you turn on a flashlight aimed at the opposite edge, more than 8 hours would pass before a single photon from your flashlight arrived. You could have breakfast, work a full day, eat dinner, and go to sleep, and the light would still be in transit, racing at 300,000 kilometers per second through the tenuous plasma of the star's outer atmosphere. These are not just numbers. These are invitations to all. Now, let us ask a question that may seem simple, but is in fact profoundly deep. What is it like inside Stephenson 2 to 18? If you could somehow journey to this star, shield yourself from its radiation, and travel from its outer atmosphere to its core, what would you experience? The answer is, in many ways, nothing like what you might expect. Begin at the outermost edge, if such an edge can even be defined. The surface of Stephenson 2 to 18 is not a surface at all, not in any way that our earthly intuitions would recognize. There is no solid ground, no liquid ocean, no sharp boundary between star and not star. Instead, there is a gradual, imperceptible transition from the near vacuum of interstellar space into an ever so slightly denser gas. Imagine walking from a desert into a very light fog. At first, you notice nothing. The air seems unchanged. But step by step, the fog thickens, imperceptibly at first, then gradually more noticeably, until eventually you are surrounded by a dense, warm, glowing mist. This is, very roughly, what it would be like to approach the outer atmosphere of a red supergiant. The outermost layers are so tenuous that they barely qualify as a gas. Their density is lower than the best laboratory vacuum we can create on Earth. You could fly a spaceship to the outer reaches of Stephenson 2 to 18 and, for a long time, you might not even know you were inside a star. The material would be too thin to see, too sparse to feel, too ethereal to register on anything but the most sensitive instruments. But as you travel deeper, and remember, you will be traveling for a very long time, because this star is larger than the orbit of Saturn, the density would slowly increase. The gas around you would grow warmer, more luminous, more tangible. You would begin to see a soft, pervasive red glow, not the harsh white light of a flame or an arc welder, but a deep, rich, cherry red, like iron heated in a forge. This is the light of a 3,000-degree surface, and it is everywhere. There are no shadows inside a star. Light comes from all directions at once. You are embedded in the source of illumination. The concept of day and night has no meaning here. You are inside the lab. Deeper still, and the conditions intensify. The temperature rises, the density increases, the light shifts from red toward orange, toward yellow. Convection currents, vast, turbulent cells of rising hot gas and sinking cooler gas, churn through the star's interior, mixing material from different depths, carrying energy from the nuclear burning core outward toward the surface. These convection cells in a red supergiant are not small. On the Sun, convection cells are roughly 1,000 kilometers across. In a red supergiant like Stephenson 2 to 18, they may span a significant fraction of the star's entire radius. Imagine a single bubble of rising gas larger than the entire orbit of the Earth. This is the scale of convection in a stellar colossus. These enormous cells are one of the reasons why red supergiants often appear slightly irregular in shape when observed with high-resolution imaging. They are not perfectly spherical. They are lumpy, asymmetric, seething with turbulent motion, living things, in a sense, dynamic and restless even as they approach their final moments. Continue your journey inward, past the convection zone, deeper and deeper into the star's interior. The temperature continues to rise. The density increases enormously. You are now in a regime that bears no resemblance to anything on Earth. The pressure is millions of times atmospheric. The temperature is tens of millions of degrees. Matter at this depth is a fully ionized plasma, electrons stripped from their atoms, nuclei moving freely in a sea of unimaginable energy. And here, at the very heart of the star, is the engine that powers it all, the nuclear burning core. In a star the size and evolutionary stage of Stephenson 2 to 18, the core has already burned through its hydrogen. It is burned through its helium. It may be burning carbon, or neon, or oxygen, or even silicon, each successive fuel lasting a shorter and shorter time, each producing heavier elements, each bringing the star one step closer to its inevitable fate. The core of such a star is an onion of nuclear ash, layered shells of different elements stacked like geological strata, each shell the product of a different fusion reaction, each burning at a different temperature, each lasting for a different duration. At the very center, an inert core of iron is growing. Iron, the endpoint of exothermic nuclear fusion, the element that cannot be burned for energy, the element that spells the doom of every massive star. When the iron core reaches a critical mass, approximately 1.4 times the mass of the Sun, a limit known as the Chandrasekhar mass, it will collapse. Not slowly, not gently, but catastrophically, in a fraction of a second. The core will implode at a significant fraction of the speed of light. Electrons will be crushed into protons to form neutrons, and a neutron star, or possibly a black hole, depending on the mass, will form at the center. The infalling material will bounce off this newly formed compact object, generating an unimaginably powerful shockwave that will tear through the star from the inside out, ripping it apart in a supernova explosion that will, for a few weeks, outshine an entire galaxy of hundreds of billions of stars. Every atom in the outer layers of Stephenson 2 to 18, every atom of carbon and oxygen and silicon and calcium that was forged in its nuclear furnace over millions of years, will be blasted into space, seeding the interstellar medium with the raw materials for new stars, new planets, new possibilities. This is how stars die. This is how the universe recycles itself. And this is the fate that awaits the Behemoth. But that day has not yet come. For now, Stephenson 2 to 18 still burns. It still swells. It still hangs in the sky above the plane of the Milky Way's disk, a smoldering crimson giant visible only in infrared, hidden from our naked eyes by 20,000 light-years of gas and dust and intervening stars. And it is, for the moment, the largest star we know. Let us now turn to a question that sounds simple but reveals, upon examination, the full depth and complexity of stellar astrophysics. Why is Stephenson 2 to 18 so large? What combination of mass, age, composition, and physical processes has inflated this particular star to dimensions that surpass all others in our catalogs? The answer lies in the interplay of several factors, and to understand them, we must delve more deeply into the physics of stellar evolution, the life cycle of a massive star, from birth to death, from compact protostellar core to bloated red supergiant to cataclysmic supernova. First, mass. The initial mass of a star, the mass it is born with, the mass of the protostellar cloud that collapsed to form it, is the single most important factor determining its fate. Mass determines how hot the core will become, which nuclear fuels it will burn, how quickly it will burn them, how luminous it will be, how long it will live, and how it will die. For the most massive stars, those born with more than about 25 or 30 solar masses, the post-main sequence evolution is particularly dramatic. These stars do not merely become red giants, like our Sun eventually will. They become supergiants. Their outer layers expand to truly enormous radii, driven outward by a combination of intense radiation pressure from the luminous core and the peculiarities of their internal structure, particularly the development of deep convective envelopes that transport energy from the interior to the surface with tremendous efficiency. Stephenson 2 to 18 was almost certainly born as a very massive star, perhaps 30 to 40 solar masses, or possibly more. Over the course of its main sequence lifetime, which, for a star of this mass, would have been only a few million years, perhaps 10 million at most, it burned through its hydrogen at a prodigious rate, converted it to helium, and then, when the hydrogen was exhausted, began the sequence of post-main sequence evolutionary stages that have brought it to its current state. It has swollen from a relatively compact blue or blue-white main sequence star, perhaps 10 to 20 times the radius of the Sun in its youth, to its current radius of over 2,000 solar radii. It has expanded by a factor of more than 100. Its surface has cooled from tens of thousands of degrees to roughly 3,000 degrees. It has transformed, utterly and completely, from a hot, compact, vigorous young star into a cool, bloated, slowly dying elder. But mass alone does not explain why Stephenson 2 to 18 is larger than other red supergiants of comparable mass. Other factors are at play. One is metallicity, the fraction of the star's material that consists of elements heavier than hydrogen and helium. In astrophysics, every element heavier than helium is called a metal, a convention that would make a chemist cringe, but that has deep historical roots in the field. Metallicity affects the opacity of the star's outer layers, how effectively those layers absorb and re-radiate energy. Higher metallicity generally means higher opacity, which means the outer layers trap radiation more effectively, which means they are pushed outward more strongly, which means the star expands to a larger radius. The environment in which Stephenson 2 to 18 formed, the Scutum Centaurus arm of the Milky Way, a region rich in gas and dust and heavy elements from previous generations of stars, may have provided it with a relatively high metallicity, contributing to its extreme size. Another factor is the star's evolutionary stage. Not all red supergiants are the same size at the same mass. A star's radius evolves over time as it burns through successive nuclear fuels in its core. During certain evolutionary phases, particularly during the transition from one nuclear fuel to the next, when the star's internal structure is undergoing rapid adjustment, the outer layers can expand significantly, reaching a temporary maximum radius that may exceed the star's eventual steady-state red supergiant size. It is possible that we are observing Stephenson 2 to 18 at or near one of these transit maxima, a moment in its life when its outer layers have ballooned to their greatest extent before contracting slightly as the core settles into a new equilibrium. Mass loss is another critical factor. Red supergiants lose mass at prodigious rates. Their outer layers are so weakly bound, so far from the gravitational center of the star, so tenuous, so easily disturbed by radiation pressure and convective motions, that they are constantly being eroded away, shed into space in a slow, steady stellar wind. The most extreme red supergiants may lose mass at rates of 10 to the minus 4, or even 10 to the minus 3 solar masses per year, meaning they shed an entire sun's worth of material every few thousand years or less. This mass loss affects the star's structure. As the star loses mass, its outer layers become even more weakly bound, potentially allowing them to expand further. There is a complex feedback loop between mass loss and radius, and in extreme cases, this feedback may help explain why certain stars, like Stephenson 2 to 18, achieve radii that are significantly larger than theoretical models would predict for a given initial mass. Rotation may also play a role, though its effects are more subtle and less well understood. A rapidly rotating star may mix material from its core to its surface more efficiently, altering the chemical composition of its outer layers, changing its opacity and energy transport properties, and ultimately affecting its radius. The interaction between rotation, mass loss, and internal mixing is one of the great unsolved problems in stellar astrophysics, and it is particularly relevant for the most massive, most extreme stars. And then there is the question of binarity. Many, perhaps most, massive stars are born in binary or multiple systems, orbiting one or more companion stars. Interactions between binary companions can profoundly affect the evolution of both stars. Mass transfer from one star to the other can change their masses, luminosities, and radii. Tidal forces can alter their rotation rates. Mergers between two stars can create a single, more massive star with unusual properties. It is not known whether Stephenson 2 to 18 has or had a binary companion, but if it did, that interaction could have contributed to its extreme size. A star that gained mass from a companion during its main sequence phase, for example, might evolve to a larger red supergiant radius than a single star of the same initial mass. All of these factors, mass, metallicity, evolutionary stage, mass loss, rotation, binarity, combine in complex, nonlinear ways to determine the final size of a red supergiant. Stephenson 2 to 18 sits at the extreme end of this parameter space, in a region where all of these factors apparently conspire to produce the most extended stellar atmosphere ever observed. It is a statistical outlier, a 1 in a billion combination of circumstances that has produced an object of truly superlative size. And yet, it obeys the same physics as every other star. There is no magic here, no special mechanism, no unique force that acts only on Stephenson 2 to 18. It is simply the most extreme product of the same processes that govern every star in the universe. This is one of the most profound insights of modern astrophysics. The universe is governed by a small set of fundamental physical laws: gravity, electromagnetism, the strong and weak nuclear forces, and from these simple foundations, an astonishing diversity of phenomena emerges. The same gravity that holds you to the surface of the Earth is the gravity that collapses a molecular cloud into a protostar. The same nuclear physics that powers a hydrogen bomb is the nuclear physics that powers the sun. The same thermodynamics that governs the flow of heat in your kitchen stove governs the energy transport in the interior of Stephenson 2 to 18. The scale is different. The conditions are different. But the underlying physics is the same. And from these universal laws, the universe constructs objects that range from dust grains a thousandth of a millimeter across to stars larger than planetary systems, from temperatures near absolute zero in the voids between galaxy clusters to hundreds of millions of degrees in the cores of massive stars. The range of phenomena that these simple laws can produce is, in a very real sense, infinite. And Stephenson 2 to 18 sits near one end of that range, the end of the largest, the most extreme, the most magnificent things that stars can be. Let us now consider the cluster in which Stephenson 2 to 18 resides, because the environment of a star is part of its story, and the environment of this star is itself remarkable. Stephenson 2 is one of the most massive open star clusters in the Milky Way galaxy. Open clusters, as opposed to globular clusters, which are ancient, dense, spherical collections of hundreds of thousands to millions of stars, are relatively young, loosely bound associations of stars that form from the same molecular cloud. They are the stellar equivalent of a family, a group of siblings born at roughly the same time, from the same material, but with different masses and therefore different fates. Stephenson 2 is estimated to contain at least 26 red supergiants, an extraordinarily high number for a single cluster. Most open clusters contain 0, 1, or at most a few red supergiants at any given time, because red supergiants are a brief phase in a massive star's life, and most massive stars and a cluster will be at different evolutionary stages at any given moment. The fact that Stephenson 2 contains so many red supergiants simultaneously suggests two things. First, that the cluster is very massive, containing a large number of stars with initial masses high enough to produce red supergiants, and second, that the cluster is at an age, estimated to be roughly 15 to 20 million years, when many of its most massive members are simultaneously in the red supergiant phase. This is a fleeting cosmic moment. A few million years earlier, these stars would still have been on the main sequence. A few million years from now, many of them will have exploded as supernovae, leaving behind neutron stars or black holes, and the cluster will be a very different place. The concentration of red supergiants in Stephenson 2 makes it a uniquely valuable laboratory for studying the late stages of massive stellar evolution. By observing many red supergiants of similar age and composition but different masses, astronomers can test their theoretical models of stellar evolution, comparing predicted and observed luminosities, temperatures, and radii. Stephenson 2-18, as the most extreme member of this cluster, provides a particularly stringent test of these models, a challenge to our understanding of how the most massive stars evolve and how large they can become. The cluster is located approximately 20,000 light-years from Earth, in the direction of the constellation Scutum, near the center of the Scutum-Centaurus arm, one of the major spiral arms of the Milky Way. This location places it behind several kiloparsecs of interstellar dust, which heavily obscures the cluster at visible wavelengths. In optical light, Stephenson 2 is virtually invisible. You could point the largest optical telescope in the world at its location and see little more than a faint, reddened smudge, if you could see anything at all. It is only in the infrared, particularly in the near-infrared and mid-infrared bands, at wavelengths of 1 to 20 micrometers, that the cluster and its constituent stars become clearly visible. This is why the cluster was not discovered until 1990, despite being one of the most massive in the galaxy. It was hiding in plain sight, concealed by the very galaxy of which it is a part. The interstellar dust that obscures Stephenson 2 is itself a fascinating subject. Dust in the astronomical sense is not the dust you find under your furniture. It is a collection of microscopic solid particles, typically a few tenths of a micrometer in size, composed of silicates, carbon compounds, and sometimes ice, that pervade the interstellar medium. These dust grains are the detritus of stellar death. They are formed in the outflows of aging stars, in the ejecta of supernovae, in the dense, cool regions of molecular clouds where atoms can combine into solid particles. And they have a profound effect on our ability to observe the universe. Dust scatters and absorbs short-wavelength light, blue and ultraviolet, far more effectively than long-wavelength light, red and infrared. This is why the setting sun appears red. Its light is passing through a long path of Earth's atmosphere, and the blue wavelengths are preferentially scattered away, leaving only the longer, redder wavelengths to reach your eyes. In exactly the same way, the light of distant stars passing through interstellar dust is reddened and dimmed, preferentially losing its blue and ultraviolet components and arriving in our telescopes redder and fainter than it would be without the dust. For Stephenson 2-18, the dust extinction is severe. It is estimated that the dust between us and the star absorbs many magnitudes of visual light, dimming the star by a factor of hundreds or thousands in the visible band. Without this dust, Stephenson 2-18 might be faintly visible to the naked eye, despite its enormous distance. With the dust, it is invisible at optical wavelengths and can only be studied in the infrared. This is a humbling reminder of the limitations of our senses and the importance of developing new technologies to extend them. The human eye, wonderful as it is, sees only a narrow sliver of the electromagnetic spectrum. The universe is full of phenomena, from radio waves to gamma rays, that are completely invisible to us without instruments. Stephenson 2-18 is one such phenomenon. It is there. It is real. It is enormous beyond imagination. But you will never see it with your naked eyes. It exists for us only through the mediation of technology, infrared detectors, digital cameras, spectrographs, computers, the prosthetic senses that humanity has built to extend its reach into the cosmos. Let us now return to the star itself and consider its future. What will happen to Stephenson 2-18? How will its story end? The answer, as I have hinted, is a supernova, one of the most violent and energetic events in the universe. But the specifics of that event depend on details that are not yet fully understood, and the possible outcomes are more varied and more dramatic than you might expect. The most straightforward scenario is a core collapse supernova. As Stephenson 2-18 continues to burn through successive nuclear fuels, carbon, neon, oxygen, silicon, an iron core grows at its center. When this iron core reaches the Chandrasekhar mass, it will collapse, bounce, and generate the supernova shockwave that will destroy the star. The outer layers will be ejected into space at thousands of kilometers per second, creating an expanding shell of hot, luminous gas, a supernova remnant that will remain visible for thousands of years before eventually fading and merging with the interstellar medium. At the center, a neutron star will form, a city-sized ball of matter so dense that a teaspoon of it would weigh as much as a mountain, spinning rapidly, emitting beams of radiation like a cosmic lighthouse. But there is another possibility, one that is perhaps even more dramatic. If the core of Stephenson 2-18 is massive enough, the collapse may not stop at a neutron star. The infalling material may overwhelm even the strong nuclear force that supports neutron star matter, and the core may collapse all the way to a black hole. This is the end that awaits the most massive stellar cores, those that exceed approximately 3 solar masses after the supernova explosion. A black hole is a region of space-time so curved by mass that nothing, not light, not information, not even time as we understand it, can escape from within its event horizon. If Stephenson 2-18 produces a black hole, the event may be accompanied by a particularly energetic explosion, perhaps a hypernova, releasing an order of magnitude more energy than a typical supernova, or possibly even a long-duration gamma-ray burst, one of the most energetic events in the known universe. There is also the intriguing possibility that Stephenson 2-18 may not produce a typical supernova at all. Some theoretical models suggest that the most massive red supergiants may undergo failed supernovae, events in which the core collapses to a black hole, but the supernova shockwave fails to propagate through the star's enormous envelope, and the outer layers fall inward rather than being ejected. In this scenario, the star would simply vanish. It would dim and disappear over a period of months or years, leaving behind a black hole with no spectacular explosion, no luminous remnant, no expanding shell of debris. The star would, in effect, wink out of existence, swallowed by the black hole it created at its own center. This would be an eerie, anticlimactic end for such an enormous star, not a bang but a whimper, not a supernova but a disappearance. Observations of several candidate failed supernovae in other galaxies have lent some support to this possibility, though the evidence is still debated. The uncertainty about Stephenson 2-18's eventual fate reflects a broader uncertainty in our understanding of massive stellar death. Despite decades of theoretical work and observational progress, the physics of core collapse supernovae is fiendishly complex. It involves general relativity, nuclear physics, neutrino transport, magnetohydrodynamics, turbulence, and a host of other physical processes that interact in ways that are difficult to model even with the most powerful supercomputers available today. The question of which massive stars produce neutron stars, which produce black holes, which explode as supernovae, and which collapsed quietly is one of the great open questions in astrophysics. Stephenson 2-18, whenever it finally meets its end, will be a data point in the resolution of that question, a single event, watched from 20,000 light-years away, that will tell us something about the fundamental physics of matter under the most extreme conditions that nature can produce. But let us not rush to the ending. Let us linger, for a while, in the present, in the majesty of the star as it exists now, burning and swelling and shedding its outer layers into the cold vastness of space. There is something deeply moving about a red supergiant. It is a star that knows, in some sense, that it is dying. Not consciously, of course. Stars do not think, do not feel, do not know. But in the language of physics, a red supergiant is a star that is past the point of no return. It has exhausted its primary fuel. It is burning its reserves, each successive fuel lasting for a shorter and shorter time, millions of years for hydrogen, hundreds of thousands for helium, hundreds for carbon, a year for neon, a few months for oxygen, a day for silicon. The acceleration is relentless. Each stage goes faster than the last. Each stage brings the star closer to the end. There is a terrible beauty in this, a grandeur in the spectacle of something so vast and so powerful winding down, stage by stage, toward its final, violent transformation. And as it dies, it gives. This is the great gift of massive stars to the universe. The elements forged in Stephenson 2-18's nuclear furnace, the carbon, the oxygen, the nitrogen, the silicon, the iron, the calcium, the magnesium, will be scattered into space when the star explodes. These elements will mix with the surrounding interstellar gas. They will be incorporated into new molecular clouds. They will collapse, under gravity's patient guidance, into new stars and new planets. And on some of those planets, perhaps, these elements will arrange themselves into molecules of extraordinary complexity, amino acids, nucleotides, lipids, proteins, the molecular machinery of life. You and I are made, quite literally, of atoms that were forged in the cores of massive stars that exploded billions of years ago. The calcium in your bones, the iron in your blood, the oxygen in every breath you take, these atoms were created in stellar interiors, scattered by supernovae, gathered into a molecular cloud, collapsed into a protoplanetary disk, accreted into a rocky planet, and eventually incorporated into a living body that now sits here, reading about the star that created them. This is the cosmic cycle of matter, the great recycling program of the universe, and Stephenson 2-18 is a participant in that program, a factory of elements, a contributor to the chemical enrichment of the galaxy, a midwife to future solar systems. Carl Sagan famously said that we are star stuff, that the cosmos is within us, that we are a way for the universe to know itself. This is not poetry alone. It is a statement of literal, physical fact. Every atom of carbon in every organic molecule in your body was once inside a star. Every atom of oxygen you breathe was fused from lighter elements in a stellar core. The iron in the hemoglobin that carries oxygen through your bloodstream was the last element fused in the core of a massive star before that star's catastrophic death. You are, in the most concrete and material sense imaginable, made of dead stars. And Stephenson 2-18, when it dies, will contribute its own atoms to the next generation, the next round of stars, planets, and perhaps life. Its death, when it comes, will not be an ending. It will be a transformation, a transmutation, a moment of creative destruction from which new complexity will emerge. Let us now broaden our perspective and ask, is Stephenson 2-18 truly the largest star in the universe? The honest answer is, we do not know. What we can say, with confidence, is that it is the largest star in the observable universe that we have been able to identify and measure. But the observable universe is a finite volume, a sphere roughly 93 billion light-years in diameter, defined by the distance that light has traveled since the Big Bang, accounting for the expansion of space. Beyond this horizon, there may be more universe, perhaps an infinite amount more, that we cannot see because its light has not yet had time to reach us. In that unseen vastness, there may be stars even larger than Stephenson 2-18. There is no law of physics that prohibits it. The upper limit on stellar size is set by the physics of stellar structure, the balance between gravity, radiation pressure, convective energy transport, and mass loss. And while we believe we understand these physics reasonably well, our understanding may be incomplete. There may be combinations of conditions, exotic metallicities, unusual mass loss histories, rare binary interactions, that could produce a star larger than any we have yet observed. Even within the Milky Way, our survey is incomplete. We have not catalogued every red supergiant in the galaxy. Many are hidden behind dust, like Stephenson 2-18 itself, and some may be in regions that we have not yet surveyed with sufficient sensitivity in the appropriate infrared wavelengths. The galaxy contains on the order of 100 billion to 400 billion stars, and while the vast majority are small, cool, long-lived red dwarfs that will never become supergiants, the handful that are truly enormous may include some that we have not yet found. The next generation of infrared telescopes, including space-based observatories with unprecedented sensitivity and angular resolution, may well discover red supergiants that rival or exceed Stephenson 2-18 in size. The current record may stand for years or decades, or it may be broken next year. Such is the nature of exploration at the frontier of knowledge. There is also the philosophical question of what we mean by largest star. Size, in the context of a red supergiant, is not a simple concept. These stars do not have hard edges. Their outer atmospheres grade smoothly into the surrounding interstellar medium, with no sharp boundary marking where the star ends and space begins. The radius we quote for a red supergiant is typically the radius at which the optical depth, a measure of how opaque the gas is, reaches a value of 2/3, which is a conventional definition of the photosphere. But this is a convention, not a physical boundary. If you define the star's edge differently, using a different optical depth, or a different wavelength, or a density threshold, you would get a different radius. For a star like Stephenson 2-18, whose outer atmosphere is extraordinarily tenuous and extended, these differences can be significant. The star is larger or smaller depending on how you choose to measure it, and this ambiguity is an inherent feature of the object, not a flaw in our measurements. Moreover, red supergiants pulsate. They are not static objects with fixed radii. They expand and contract on timescales of months to years, driven by complex interactions between convection, radiation, and the opacity of their outer layers. Betelgeuse, the nearest bright red supergiant, and the one we understand best, varies in brightness by roughly a factor of 2 over a period of approximately 400 days, corresponding to significant changes in its apparent size. Stephenson 2-18 is almost certainly variable as well, though its variability is less well characterized due to its extreme distance and heavy dust obscuration. The radius we quote for it is a snapshot, a measurement made at a particular time, during a particular phase of the star's pulsation cycle. At another time, the star might be somewhat larger or somewhat smaller. The universe does not hold still for our measurements. All of this should not diminish the achievement of identifying Stephenson 2-18 as the largest known star. It should, rather, deepen our appreciation for the complexity and subtlety of the natural world. The universe is not a collection of simple objects with fixed, easily measured properties. It is a dynamic, evolving, endlessly surprising place where even the most basic questions, how big is that star, lead down rabbit holes of physics, observation, and philosophy that have no clear bottom. This is what makes science beautiful. Not the answers, but the questions. Not the facts, but the journey of discovering them. Let us spend a moment contemplating the light of Stephenson 2-18, the actual photons that leave its surface and travel across 20,000 light-years of interstellar space to reach our telescopes. These photons are travelers. Each one begins its journey deep within the star, generated by the nuclear reactions in the core. But a photon born in the core of a star does not simply fly straight outward to the surface and into space. The interior of a star is opaque, so dense, and so hot that photons are constantly being absorbed and re-emitted by the surrounding plasma. A photon generated in the core of Stephenson 2-18 will be absorbed by a nearby atom or ion within a fraction of a second, re-emitted in a random direction, absorb again, re-emitted again, absorb again, re-emitted again, performing a random walk, a drunken stagger, to the star's interior. The average photon generated in the core of our Sun takes approximately 170,000 years to reach the surface, despite the fact that the Sun's radius is only 2 light seconds. In a star the size of Stephenson 2-18, with a radius over 2,000 times larger than the Sun's, the journey from core to surface takes far longer, millions of years, possibly tens of millions, for a single photon to random walk its way from the nuclear furnace to the cool, tenuous surface where it can finally escape into space. Think about what this means. The infrared light that we detect from Stephenson 2-18 today, the light that our telescopes are capturing right now, was generated by nuclear reactions that occurred millions of years ago, deep in the star's core, when the star was in a different evolutionary state than it is today. By the time those photons reach us, they carry information about the star's past, not its present. We are always seeing stars as they were, never as they are. And for Stephenson 2-18, the delay is compounded. The photons were generated millions of years before they reached the surface, and then they traveled for 20,000 years through interstellar space before reaching our telescopes. The light we see is ancient even by the star's own standards. And then there is the further, almost vertiginous realization that the star itself is 20,000 light-years away, which means the light we are receiving now left the star 20,000 years ago. When those photons departed Stephenson 2-18's surface, the last ice age was ending on Earth. Humans were painting caves in Lascaux. Agriculture had not yet been invented. Writing did not exist. Civilization, in any recognizable form, did not exist. The entire history of human civilization, from the first cities in Mesopotamia to the smartphone in your pocket, has occurred in the time it took that light to reach us. And in all that time, those photons traveled through the void at the speed of light, crossing the vast, cold, empty spaces between the stars, passing through dust clouds and alongside other stellar systems, carrying their tiny payload of information about a colossal, dying star toward a planet where, eventually, someone would build a telescope to receive them. There is an intimacy in this act of observation that we rarely acknowledge. When you look at a distant star, really look at it with understanding, you are not merely seeing a point of light. You are participating in a communion across time and space. Photons that were born in the nuclear heart of a star 20,000 years ago have crossed an unimaginable gulf to end their journey on the retina of your eye, or on the sensor of your detector, and in that moment, the star and the observer are connected by a thread of light that spans millennia and parsecs. This is what astronomy is, at its deepest level. It is not merely the study of distant objects. It is the act of receiving messages from the cosmos, messages written in light, carried across the void, and decoded by the curious minds of a species that has existed for an eye blink of cosmic time. Let us now consider the broader context of stellar size, the full spectrum of star sizes that the universe has produced, from the smallest to the largest, and where Stephenson 2 to 18 fits within that spectrum. Stars come in an astonishing range of sizes, from tiny red dwarfs barely larger than Jupiter to the red hypergiant leviathans we have been discussing. The smallest known stars are at the boundary between stars and brown dwarfs, objects that are massive enough to sustain hydrogen fusion, but only barely. The smallest true star might have a radius of roughly 80 to 90% of Jupiter's radius, perhaps 100,000 kilometers or so. This is about 1/10 the radius of our Sun, and about 1/50,000th the radius of Stephenson 2 to 18. The difference in volume between the smallest star and the largest star is a factor of approximately 125 billion. 125 billion. The universe produces stellar objects that span more than 4 orders of magnitude in radius and more than 11 orders of magnitude in volume, all using the same basic physical processes: gravitational collapse, nuclear fusion, and the eternal tug-of-war between gravity and pressure. On the main sequence, the band in the Hertzsprung-Russell diagram, where stars spend most of their lives stably burning hydrogen, the range of radii is more modest. The smallest main sequence stars, the N-type red dwarfs, have radii of roughly 0.1 to 0.6 solar radii. The Sun, a G-type star, has a radius of exactly 1 solar radius by definition. The hottest, most massive main sequence stars, the O-type blue supergiants, can have radii of 10 to 20 solar radii or more. But it is only when stars leave the main sequence, when they exhaust their core hydrogen and begin their post-main sequence evolution, that truly enormous sizes become possible. The expansion to red giant or red supergiant dimensions is a consequence of the star's internal restructuring, and the maximum size achieved depends on the star's mass, composition, and evolutionary history, as we have discussed. Within the Milky Way alone, there are estimated to be on the order of a few hundred to a few thousand red supergiants at any given time, out of a total stellar population of hundreds of billions. Red supergiants are rare. They are the product of massive stars, which are themselves rare. The stellar mass function is heavily weighted toward low-mass stars, with high-mass stars being exponentially less common. And even among the red supergiants, only a tiny fraction achieve the extreme sizes of Stephenson 2 to 18, or its closest rivals. These are the most exceptional products of ordinary stellar evolution, the tallest peaks in a mountain range, the deepest notes in a symphony, the rarest and most extreme manifestations of the physical laws that govern all stars. It is worth noting that size is not the same as mass, and the largest stars are not the most massive. The most massive known stars, objects like our 136A1 in the Large Magellanic Cloud, which may have a current mass of over 200 solar masses, are not red supergiants at all. They are hot, blue, compact stars, burning hydrogen on the main sequence or in its immediate aftermath. Their radii are large by ordinary standards, perhaps 30 to 40 solar radii, but tiny compared to the red supergiants. Mass and radius are related, but not in a simple, linear way. The most massive stars are the most luminous, but they achieve their luminosity through high temperature, not large size. It is only when a massive star evolves off the main sequence and becomes a red supergiant that its radius balloons to thousands of solar radii, and by that point, The star has lost a significant fraction of its initial mass to stellar winds, so the red supergiant phase represents a lower mass, but much larger, version of the star's former self. This distinction between mass and size is crucial for understanding the nature of Stephenson 2-18. It is among the largest stars in the universe, but it is not among the most massive. Its current mass is estimated at somewhere between 15 and 25 solar masses, far less than the most massive known stars, and probably far less than its own initial mass at birth. It has shed enormous quantities of material over its lifetime, losing mass to its stellar wind at rates that may have stripped away half or more of its original mass. The mass that it has lost is now drifting through space, forming a diffuse circumstellar envelope around the star, enriching the interstellar medium with the products of nuclear fusion. What remains is a relatively low-density, enormously extended ball of plasma, a star that is vast but tenuous, like a soap bubble the size of a solar system. Its average density is astonishingly low, far lower than the air you are breathing right now, lower than the best vacuum achievable in a laboratory. If you could somehow weigh a cubic meter of Stephenson 2-18's outer atmosphere, it would weigh less than a cubic meter of the near vacuum inside a fluorescent light tube. The star is, in a very real sense, mostly empty space. It is a ghost of its former self, a shadow of the compact, dense, powerful star it once was, inflated to dreamlike proportions by the physics of its own dying. This is one of the most poetic aspects of stellar evolution, the relationship between power and fragility, between enormity and ephemerality. The largest stars in the universe are also the most temporary. Stephenson 2-18, for all its mind-bending size, will exist as a red supergiant for a cosmically insignificant period, perhaps a few 100,000 years, perhaps 1,000,000 at most, out of a total stellar lifetime of perhaps 10 to 20 million years. Compare this to a red dwarf like Proxima Centauri, the nearest star to our Sun, which will burn steadily for perhaps 4 to 6 trillion years, more than 300 times the current age of the universe. Proxima Centauri is tiny, dim, unremarkable by any visual measure. But it will still be burning when all the red supergiants that exist today have long since exploded and dissipated. The tortoise and the hare, played out on a cosmic stage. There is a lesson in this, if we care to look for it. A lesson about the nature of permanence and impermanence, about the relationship between spectacle and duration, about the choices that nature makes, or rather, the choices that physics imposes, on the objects it creates. The universe does not optimize for longevity. It does not optimize for beauty, or size, or power. It simply follows its laws, and those laws produce a distribution of outcomes, some brief and brilliant, others long and quiet, all equally valid, all equally real, all equally part of the grand tapestry of cosmic evolution. Let us now turn our attention to the tools and techniques that astronomers use to study stars like Stephenson 2-18, the instruments and methods that allow us to determine the size, luminosity, temperature, and mass of an object 20,000 light-years away. This is, in many ways, the most remarkable part of the story, because it demonstrates the extraordinary power of human ingenuity. We cannot visit Stephenson 2-18. We cannot touch it, sample it, or examine it directly. We have only its light, the photons that make the 20,000-year journey to our telescopes, and from that light, we must infer everything we know about the star. It is like trying to determine the size, weight, and temperature of a bonfire by studying the pattern of light and shadow it casts on a wall miles away. And yet, we can do it. We can do it with remarkable precision. And the methods by which we do it are among the most elegant creations of the human mind. The most fundamental tool is spectroscopy, the analysis of the spectrum of light emitted by a star. When you pass starlight through a prism or a diffraction grating, it spreads into a rainbow of colors, a spectrum, and embedded in that spectrum are dark lines, absorption features at specific wavelengths where atoms in the star's atmosphere have absorbed photons of particular energies. These absorption lines are the fingerprints of elements. Each element produces a unique pattern of lines, and by identifying these patterns in a star's spectrum, astronomers can determine the chemical composition of the star's atmosphere. But that is only the beginning. The exact positions of the absorption lines tell us the star's radial velocity, its speed toward or away from us, through the Doppler effect. The widths of the lines tell us about the temperature, density, and turbulent motions in the atmosphere. The relative straits of lines from different ionization states of the same element tell us the temperature more precisely. And the overall shape of the spectrum, the distribution of energy across wavelengths, tells us the star's effective temperature, which, combined with the luminosity, gives us the radius to the Stephenson-Boltzmann law. For Stephenson 2-18, spectroscopy in the infrared is essential, because the star's peak emission is in the infrared, and its visible light is heavily absorbed by interstellar dust. Infrared spectra of red supergiants show a rich forest of molecular absorption features, bands of titanium oxide, water vapor, carbon monoxide, and other molecules that form in the cool outer atmospheres of these stars. By modeling these molecular features, astronomers can determine the star's effective temperature with a precision of a few hundred Kelvin, not perfect, but sufficient to constrain the size estimate within reasonable bounds. Photometry, the measurement of a star's brightness at specific wavelengths, is another essential tool. By measuring Stephenson 2/18 brightness in multiple infrared bands and comparing the observed brightnesses to what would be expected for a star of a given temperature, astronomers can determine the amount of interstellar dust extinction along the line of sight and correct for it. This is a critical step, because without accurate dust correction, the luminosity estimate would be wrong, and the size estimate would be wrong as well. The dust correction is one of the major sources of uncertainty in the size estimate for Stephenson 2-18, and improving our understanding of the dust toward the Scutum Centaurus arm is one of the key goals of ongoing observational programs. Interferometry, the technique of combining light from multiple telescopes to achieve the angular resolution of a single, much larger telescope, has been used to directly measure the angular sizes of some of the nearest and largest red supergiants, most notably Betelgeuse. In principle, interferometry could also be applied to Stephenson 2-18, but in practice, the star is too distant and too heavily obscured for current interferometric facilities to resolve. Its angular size, as seen from Earth, is extremely small, far smaller than the angular resolution of even the best adaptive optics systems on the largest ground-based telescopes. We cannot, at present, take a picture of Stephenson 2-18 that shows its disk. We could only infer its size from its luminosity and temperature, using the methods described above. This is a limitation, and it means that the size estimate carries inherent uncertainties. But it is the best we can do with current technology, and the estimate is robust enough to place Stephenson 2-18 securely among the largest known stars. The Gaia Space Observatory, launched by the European Space Agency in 2013, has revolutionized our understanding of stellar distances and, by extension, stellar sizes.